I said before that we don't have any physics yet. There's no physics here. I mean, I guess there's, if you can, yeah, there's not, I don't know, I'm tongue-tied a little bit, but let's inject some physics in the form of Newton's second law. And the idea is the acceleration, according to Newton's second law, the acceleration is the only kinematic thing that's related to force and mass, and it's related this way. It's the net force on a mass m divided by the mass m. So here's acceleration. There it is in this kinematic and mathematical dot product statement. So put the physics in. So the physics is that the final velocity dotted against itself is the same as the initial velocity dotted against itself plus 2 times f net dotted with delta r, or the displacement vector delta r, divided by m. And now we have this statement that, if you remember where it came from, the statement came from a kinematic ingredient that was about constant acceleration. So we have to keep this in mind, that this, strictly speaking, is true for constant acceleration. Constant acceleration is what you get when the net force is constant. So F net is a constant. That is, it's not time dependent. So in the case where F net is constant in time, then if you then that means that Newton's second law predicts this relationship between the final velocity of an object, the initial velocity of an object, and the net force acting on the object, the displacement the object moves through. So this is actually describing the difference between the final position of the mass and the initial position of the mass. So I'll write that right here. What this is it is the final position vector minus the initial position vector. That's what this delta r is. So throughout the displacement going from this location over to this location, this force was acting throughout that entire displacement, where this force does not change in time. It doesn't change during the time that this displacement is happening. Also, there's this factor of 2. So let me go and rewrite this. So we have kind of a generic statement that if you take a vector A, regardless of what A means, it could just be pure math, A dot A. Another way to write this is the magnitude of A squared. And sometimes a shorthand is to just drop the little arrow, indicating that what we're talking about is the magnitude of the vector A. That is, A equals the magnitude of the vector A. So if we use this kind of like notation or shorthand up here, this is just V final. I'll do it in a couple of steps. It is the magnitude of the final velocity squared is equal to the magnitude of the initial velocity vector squared, plus 2 times the net force acting on m divided by m, that's a vector, dotted with delta r. There's no shorthand to do over here. So now, because I'm inspired, and maybe because I went and peeked at your work Kinetic Energy Theorem chapter, right? We are studying work in kinetic energy. I'm going to take this little m, right? I'm free to do any math I want, so I'm going to multiply both sides of the equal sign by m. So here's an m, and if I multiply m here, say, they cancel, and then I'm going to divide both sides by 2. So divide by 2, divide by 2, and divide by 2. If I divide by 2 here, the 2's cancel. And then if I clean this up a little bit, I'm going to go over and use this other way to rewrite the magnitude of the a vector squared. This is 1/2 mv final squared equals 1/2 mv initial squared plus, so that the 2's and the m's are gone. This is F net dot delta R, right? And now you can see that this is the kinetic energy final. This is the definition of the final kinetic energy. It's the final velocity squared times the mass of the object times the factor 1/2. And this is the kinetic energy initial. And this right here is what's called the work done by net force, right? So what this says is that kinetic energy final, I'm going to subtract the initial kinetic energy over to this side, so minus kinetic energy initial is equal to F net delta R. So that's the net force dotted against the displacement vector, and the relationship is this equal sign, and that's a difference in kinetic energy. So on the left-hand side, we have to be super careful. It is wrong to say that the kinetic energy is F net dot delta R. What is correct, the physics is, if there is a net force that gets to act on an object over a displacement delta R, then what you're going to get is a change in the kinetic energy. There is a change in kinetic energy, and it's equal to the work done by the net force right here. So just to go and trace back for a second, we started with kinematics, Newton's second law, and a little bit of math. That is, Newton's second law really, these are the same. Like we didn't, there was no injection of any big ideas here. The idea is Newton's second law and the work energy theorem, they are compatible with each other. That is, if you define this thing called the net work, or the work done by the net force, it is equal to the change in something that's got to do with the mass and the speed squared. Yep. So we get a new perspective. And yeah, this new perspective is called the work kinetic energy theorem. So I'll just shorthand it like this. But it is based on kinematics and Newton's second law.